Now the next big thing after reflection is refraction. Now refraction is nothing but the change in the speed of the light when the light shifts from one medium to another medium. Now there are various mathematical expressions and theories governing this phenomena. So we'll first, as we did with reflection, we'll start off with refraction through plane surfaces, and then we'll shift our attention to refraction through spherical surfaces. But before that, let's start off with refraction through plane surfaces. Now let's study one of the most important phenomena associated with light, that is refraction. So starting off, we will like to know what is refraction first in a nutshell. Then we will try to find out the reason why it does that and how it does that, and what is that is we will at the end of it we'll put mathematical expressions to what we actually see. We'll not get that much into the reason. As I've told you, in ray optics we won't be bothered by the reason, rather than we will be actually looking out for how much is a change and where is it going, where will it land, where will it intersect. These are the questions which we actually want to answer. So moving on, refraction of light. Refraction is a phenomena of the change in the path of the light as it travels from one medium to another when the ray of the light is incident obliquely. Now this phenomena is pretty evident from the lines which I have just read. Is the light if traveling in one particular direction, when it actually comes across a surface beyond which I have another medium, then the light sort of changes its path, whether it moves away from a particular normal or it moves towards the normal, depending upon the two media. Why is that happening? The reason actually is that the speed of the light gets changed. That is, right now the speed of the light in this particular medium is 3 into 10 to the power 8 meter per second. Now if the same light now enters water, it will travel with a different speed. If it enters glass, it will travel with another different speed. So it changes. And I've told you we won't be getting into the reasons right now. We will be getting into the reasons in the chapter of wave optics. So right now we should actually know that the speed of the light changes when it moves from one medium to another medium. And that is what affects the path of the light. That is, it has to change its path. It can also be defined as a phenomena in which the change in the speed of the light from one medium to another medium. As I've told you, either you can define the refraction as a phenomena of change in the path of the light as it travels from one medium to another, or basically define it as a change in the speed of the light. Now, I've picked up a particular surface and a two medium in context. That is, I have a rarer medium over here, and this is a denser medium. I'll tell you in the context what is the meaning of a rarer medium and what is the meaning of a denser medium. But we will first have a look at what will happen across these two media. So the light comes in, it bends towards the normal, as you can see, and when the light is actually moving out from denser to rarer medium, it moves away from the medium, a normal. Now, rarer medium is basically a medium in which the speed of the light is more than the medium present on the other side of the surface. So let's say I have two medium, 1 and 2. If the speed of the light is greater in medium 1 than in 2, then 1 is called as a rarer medium and 2 is called as a denser medium. So rarer and denser, they are simply relative in nature. So depending upon which medium is across that surface, you might be called as rarer or you might be called as denser. So denser is where the speed of the light is smaller than the speed of the light in the medium on the other side of the surface. So based on simply the speed of the light in the medium, one is called as denser and another one is called rarer. So if light's coming from rarer medium, it refracts towards the normal, right? This is a light ray, it kind of refracts towards the normal. And when the light is moving from denser to rarer medium, so light moves away from the normal, as pretty evident over here. So
make sure that you keep this phenomena inside your head, that is from rarer to denser what happens, and from denser to rarer what happens, and also what is rarer and what is denser and difference between them. So this is IR, and as I've told you, bending towards normal, bending away from the normal. Now there are laws, as same kind of laws which we had in the reflection, which we will be put to use in case of refraction as well. So here are those laws. The first law is, let's say, the exact photocopy of the first law of reflection with simply a change in this term. The incident ray, the normal to the refracting surface at the point of incidence, and the refractive ray all lie in the same plane. That's the first law. We kind of had the similar law in case of law of reflection, where I had the incident ray, the normal to the reflecting surface at the point of incidence, and the reflected ray will all lie in the same plane. But here the phenomena is refraction, so in place of reflection I have refraction. Second is Snell's law. So it's given for a given pair of media and for a light of a given wavelength, the ratio of the sine of the angle of incidence to the sine of angle of refraction is constant. That's what Snell said. So that ratio, as we now know it, is also called as refractive index. So that constant mu is refractive index, I is the angle of incidence, R is the angle of refraction. So if you want to write out a mathematical equation corresponding to 2, here is the equation. Mu is equal to mu, the refractive index, is equal to sin I by sin R. Mu of optically rarer medium is lower and that of denser medium is higher. So again, optically rarer medium basically tells me that the speed of the light in this particular medium is kind of better than the rest of the lot, and that in the denser medium is kind of very low, or it's in the lower side of the lot. Now mu of a denser medium with respect to a rarer medium is more than 1, and that of a rarer medium with respect to a denser medium is less than 1. Now, the refractive index, as it's given or it's defined using Snell's law, is sin I by sin R, that is sine of the incident angle divided by the sine of the refracted angle. I can also relate it to the speed of the light in air or vacuum divided by the speed of the light in that particular medium. So if it means the speed of the light is reasonable, is good enough in this particular medium, then the refractive index will have a value closer to 1. And if the speed of a light in a particular medium is very low, it means the refractive index will be of a very higher value. So it means the faster you are, the faster the light is in a particular medium, the smaller will be your refractive index. So if you are going to measure the refractive index of a particular medium with respect to a medium other than air, then you might end up getting refractive index sometimes 5, 10, 12 or even 0.001, 0.0001, whatever. It depends upon what two medium are you comparing. So I can write it out, that is mu is equal to CV or mu 1, 2. If I am comparing 1 with respect to 2, then it will be V2 by V1. Speed of the light in the second medium divided by the speed of the light in the first medium. So it all depends upon the comparison which you are trying to do. In refraction, the velocity and the wavelength of light changes. As I said, the velocity changes actually because of the wavelength of the light changes. The frequency remains a constant. That's the key. My wavelength and velocity changes, but frequency remains constant. And phase of the light do not change. That's written. So I have a mu m is equal to Ca by Cm. That is, I am trying to compare medium M with respect to A. So based on that, I have tried to procure the refractive index, the refractive index of material M with respect to material A, and that's the expression which I have also written it over here. Similarly, as Ca by Cm, I know that the frequency is not changing, so substituting the relation of the speed of a wave in terms of its frequency and wavelength, I will end up getting this lambda A by lambda M. So refractive index can also be put up as a ratio of their wavelength, ratio of the light in the different wavelength, in the different medium. Principle of reversibility of light. Now, reversibility of light means I came in through a particular way, I got out in exactly the same fashion, right? So let's say I enter into a particular room, all guns blazing, firing in this particular guy, that particular guy, right? So I'm not that violent, I'm just saying that suppose we enter in that particular fashion, and suppose you play that clip backwards, can I say that it will be kind of a reversibility thing happening, right? So it's all in the reverse orders. Like bullets coming back to my guns, me putting my guns back into my pockets, and door closing by, and me moving out. So it's like things happening in reverse order. So in case of principle of reversibility of light, I undergo a similar phenomena. That is, the light comes in, arrives at a particular point, and then retraces its path. That's what's called or reversibility of light, that phenomena. For, let's say, if I want to have a mathematical expression, or let's say the condition written in the form of an equation which tells me what are the condition or parameters should be such that I end up getting a proper reversibility of light, then I need to come up with this. That is, mu A is equal to sin I by sin R. Remember, I am comparing medium A and B. So the light from A is entering B, so A mu B is sin I by sin R, or B mu A is equal to sin R by sin I. Now, all of us know that A mu B is equal, multiplied by B mu A is equal to 1 by A. So that is, these two, the product of these two is 1, or 1 is the reciprocal of the other. Now, for the principle of reversibility of light, I will work through a particular set of conditions right now. If a ray of light, after suffering any number of reflections and refraction, has its paths reversed at any stage, and it travels back to the source along the same path in the opposite direction. That's the condition, the first condition, which we have extensively discussed as a part of an example, me entering a room, all guns blazing. That's the same thing which is written over here in terms of the different phenomena the light undergoes. So let's say a light is reflected in a particular fashion, let's say like this, then it goes like this, then it kind of refracts, whatever, and ends up reaching this. And from this point onwards, the light travels back the same path, then it's a total reversibility of light. A natural consequence of the principle of reversibility is that the image and the object positions are interchanged. These positions are called as conjugate position. Now the weird part obviously is when the light is retracing its path, that is light coming from, let's say, my tip of the nose, and it's going all the way to a particular point where it undergoes total reversibility of light. From that point onwards, the light again retraces the path, reaches the same tip of my nose where the source was. So now the object and the image position can literally be exchanged because they end up lying on the same point. So these positions, they are called as conjugate position, which is very important as far as reversibility of light is concerned. Because if the object and the image are placed in a conjugate position, I might not be able to distinguish what's the object, what's the image. So in order to know where are the conjugate points is of very important while dealing with reversibility of light, because I need to make sure that object and image, they are properly separated. A refraction through a parallel slab. So we kind of observed or we have done this experiment quite a lot in our let's say small classes, class 9, 8 if you guys remember. That is, looking through a glass slab, I don't end up seeing a pen over here, I kind of see it a bit shifted like this. So the change in position through which we calculate the lateral shift and different things. So that's what we will be doing over here. So again the same mathematical expression, A mu B is sin I1 by sin R1, B mu A is sin I2 by sin R2, and this relation again is very important. A mu B multiplied by B mu A is 1. Then again, we are just trying to come up with the expression or which relates angle of incidence and angle of reflection. So this is a very basic property, and now we are trying to work out a few of the facts. Now, why we have intentionally dig in two opposite comparison, that is A mu B and B mu A, because refraction through a parallel slab involves you entering from one medium to another medium and you exiting from that same medium to the original medium. So there are two completely different and completely opposite phenomena taking place, so we need to keep that in mind. So it implies that I1 equals to R2 and I2 equals to R1, since we definitely know these are not the case. So in order to make this valid, I need to make sure that these two are equal and these two are equal, because I definitely know that I1 is not equal to R1. In that case, it's like I have no medium at all when I1 equals to R1, or in the other way around, I2 equals to R2. I cannot have these two conditions, that's for sure. So this is corresponding to this particular figure. There is an experiment which we have done quite a lot. So right now what we'll do is try to find out the lateral shift over here, which is the distance between these two lines. That's what we're trying to find out, the lateral shift. So I1, R1, I2, R2, they are different things which we have over here, and we sort of want to quantify what is the lateral shift. So lateral shift is y t delta cos R1, and delta is I1 minus R1, so we can definitely express lateral shift like this or like this, either way, depending upon the information which we have. Special case is obviously when I1 is very small, then I guess R1 also will become very small, and we can drop out the sign as well. So sin I1 minus R1 becomes I1 minus R1, and cos R1 becomes 1. So this is a small angle approximation, that is only when I1 is very small I can end up writing this expression. That is, the lateral shift is equal to the thickness multiplied by the angle of incidence minus the angle of refraction at the first surface. That's my lateral shift. Now, which I1 minus R1, which can be written in terms of the refractive index. So more or less, depending upon what's your angle of incidence, only angle of incidence, the rest parameter, the thickness and the refractive index, they are fixed. So the only factor in which I can change my lateral shift is by playing with the angle of incidence. Other than that, I need to change my medium or thickness of the slab to make sure my lateral shift is of good amount. So again, if I have put up multiple slabs with the way which I have done it over here, that is, I can put up with multiple slabs. So each one, or whatever happening in this surface, will act out for whatever incident we for this particular surface. So the exit from A to B, A to B to A will act as an, let's say, incident material for the surface between C and B. So the exit one for A and B will act as an entry one for B and C, and the final exit one will be for C and A. So nothing changes along, but other than the extra refractive index equation I need to put up. A mu B is sin I1 R1, then it will come B mu C is sin R1 by sin R2, then C mu A is equal to sin R2 by sin R1. So as you can see, we need to put up with extra equation because of the 3 medium in this particular situation. So mu C is greater than mu B, that's what we have arrived over here, and this will be 0, this will be 1. It's pretty trivial that this will be 1, then, or we can simply play along, that is, if I take C mu A to the other side, so it's 1 by mu C mu A, which comes out to be A mu C, as it's a reciprocal. So obviously we can work around, I can take out different terms to the other side again I will end up getting a symmetric expression.
Now in this simulator we will work around refraction. Primarily we will deal with refraction. So first we will verify the Snell's law over here and other aspects of refraction through the plane surfaces. So again, as you can see that when the light is incident, I choose any orientation as I like to be. So this is off, this is on. So if I choose any orientation, let's say I choose this particular angle of incidence, a part of light is reflected and a part of light is refracted. Now the angle of refraction, if you can notice, that is, again I would put this over here. So let's choose a particular angle of incidence, that is the angle of incidence which we are very comfortable with, and verify what is the refractive index. So let me change, so the index of refraction is 1 for this particular medium, and in that index of refraction is 1.5 for this particular medium. So what I will do is I will change the index of refraction for this particular medium without, or my point of eye will be over here. So I want to make sure this is sine 60. I want to make sure that the angle which comes out is one which I am comfortable with. So let me see. Okay, if I am right now decreasing, the angle of refraction is increasing. Okay, so I'll make sure that as I hit the value of 30 somewhere, if I can. No, I cannot hit the value of 30. So what I will do again, I will hit the value of something which I already know of. So this is 40 degrees and this is 45 degrees. So this is 60 and this is 45 degrees. So I know what is the value of sine 60 and I also know what is the value of sine 45. So ratio of that has to come out 1.26, and if you work it out you will end up getting exactly to be 1.26. Again 60 clearly pans out. So angle of incidence is equal to angle of reflection, angle of incidence and angle of refraction, they are related like this through the refractive index. Now if I change the refractive index of the medium in which the light was traveling, that is, let's say it's 1, that is the least value of the refractive index is 1. If I increase it, I expect the light to deviate more, or let's say the angle of reflection should increase. Let's see if that happens. Yeah, it is happening, right? It's 1.16. Then let's see what happens as exactly at 1.26. At 1.26, if you clearly notice, there is no reflection. It's like the light is in the same medium, right? Have a look at it. The light is in particularly same medium. Now again I will increase the value of, now it will bend away from the normal, because this is now the rarer medium and this is the denser medium and this is now the rarer medium. So it's bending away from the normal, again increasing it away from the normal. So this is refraction as a whole. Again, if I play along with this, increasing the refractive index, the angle of refraction decreases, it bends more towards the normal. So this is the maximum 1.6, the maximum I can go to, because I have set up 1.6 as the refractive index limit for this particular medium, and same for the above. Again I can play along with like this. So this is in a nutshell refraction through a simulator, such that you do have a visual aspect of how it looks like. So this is refraction through a plane surface, that is the refraction which we have studied till now through glass slab and all these features. This was corresponding to that. We will have a look or use more of these in studying total internal reflection as well, but that's saved up for the coming videos.
So apparent depth of liquid, a direct application of refraction through the surfaces is the change in the level of the liquid which I perceive. So here's a liquid, and obviously water is a denser medium than the air, so I'm over here looking from the top at the depth of the liquid, or trying to locate the bottommost point of the liquid in the container. So what happens is the light comes in, gets refracted. So that's one. The other light ray kind of does this. So I end up extrapolating the point and then end up getting this point as the image. So that's the point which will be perceived by my eye. That's the point which will be perceived by my eye as an image or as the bottommost point of the container, which in fact is not the reality, which is completely else. But the decrease or the fall in the apparent depth of the liquid is because of refraction. And we will calculate it out, that is B mu A is sin I by sin R, the reverse of it, A mu B sin R by sin I. And I have known that is A mu B is HR by HA, that is real depth by apparent depth. So apparent depth of a number of immiscible liquids is this. So if I have many liquids present along, I will have to get on with this expression. So I usually don't have many immiscible liquids, but the fact that is I have to put up with this mathematical expression considering multiple immiscible liquids, because in the oceans or let's say in rivers, ponds, I have a variation in the density of the liquids. Liquid being water, but as I'm moving up to down or from top to bottom, there is a change in density. So I need to put up with this expression to get the exact value of the change of depth. So apparent shift, which is actually happening in reality, that is HR minus HA, is this. HR being the real depth is multiplied by 1 minus 1 by mu will give me the apparent shift in the depth. Now comes the total internal reflection. It's a very important property as far as refraction is concerned. It has tremendous use in today's technology, data transmission and whatnot. So we'll first get to the bottom of what is total internal reflection. So total internal reflection is basically evident when the light is exiting from denser medium to a rarer medium. So usually I will have different set of light rays, hitting the surface, which is common to both rarer and denser medium. So one light ray will actually simply refract to start moving with a new direction. Other one will refract. So as I'm increasing the angle of incidence, I do see that they will move further away from the normal. Now there will come a point where the angle of refraction is such that it's 90 degrees. Now I'm right now at a particular situation where I need to think what will happen from this point onwards. That is, if I increase the angle of incidence beyond this point where I have had an angle of refraction to be 90 degrees, what will be the next thing? What happens is, if I increase my angle of incidence, it behaves as if it's like reflection. That is, angle of incidence is equal to angle of reflection. So this is called as the critical angle beyond which I have total reflection. That is, in these parts, if you look closely, in these situation, I have a part of it which was undergoing reflection and a part of it which was undergoing refraction. So an incident light ray was kind of divided into two aspects, refraction and reflection. But there comes a critical angle IC, which is given over here, for which the angle of refraction is 90 degrees. That is, if my angle of incidence is greater than the critical angle, all the light rays, all of it will undergo reflection. Not even one single light ray will undergo refraction. Everyone will undergo reflection. So that's why it's called as total internal reflection. It has got tremendous use in jewelry designing, in fiber optics, data transmission, which results into data transmission. So it's a very coveted concept which we are using it extensively nowadays. Relation between critical angle and refractive index. So obviously I actually know the condition, that is the angle of refraction is 90 degrees. So it's actually pretty easy to find out the relation between the critical angle and the refractive index. So I have G mu A is equal to sin I by sin R. Obviously, R equals to 90 degrees. I get sin IC is equal to G mu A. Or this is the expression corresponding to the total internal reflection. So, sin IC is equal to 1 by A mu G, or sin IC is equal to lambda G by lambda A. So red color has a maximum value of critical angle, whereas the violet color has the minimum value of the critical angle, since obviously the critical angle kind of depends upon the wavelength. So if you change your wavelength, your critical angle might change. So hence red, having the largest wavelength, has a maximum value of critical angle, whereas the violet, having the least of the wavelength, has the minimum value of critical angle. So I've simply substituted the refractive index, which is kind of given by Cauchy's relation over here. That is, refractive index is related to the wavelength of the light, which is a Cauchy's relation. So application of TIR, total internal reflection, mirage formation found in hot places, looming formed and found in cold places, very cold places, total reflecting prisms, obviously the fake jewelries which you guys see right now, made up of glass and these things, they are using total internal reflection to make sure it shines a lot. It's actually it's not shining a lot. They are reflecting the light through multiple surfaces so as to make one exit point where it seems that it's very shiny and it's a very rare jewelry. Other one is optical fibers. As I have told you earlier, it's used for transmitting data. So right now we are connected. You are able to buffer the video, see a particular website, browse through Facebook, stream YouTube videos, is only because literally the optical signals are being transmitted through the wires laid down in the ocean from one point to the other point, and it's carried on through the cities, and the data is transmitted in within split seconds because light is the data which is being transmitted through fiber optics. So that's a very important use of total internal reflection. Then there is sparkling of diamonds. That is, the natural diamonds, they are designed in such a fashion that they end up having total internal reflection from multiple surfaces and exit at a very specific point in their structure, so as to make it glowy, shiny and sparkling. Now we will work around total internal reflection phenomena. That is, we have to study total internal reflection. So let's figure out what is the angle at which the total internal reflection occurs, depending upon the characteristic of two medium of interest. Medium number one, the light in the medium in which the light was traveling initially, and the other one was the medium in which the light will try to travel in afterwards. So if I increase the angle of refraction, or let's say the refractive index over here, I see that the light is moving towards the normal. What I basically want is, for total internal reflection, I need to have the light traveling in a denser medium, and the light wants to travel in a rarer medium. So I will make medium number one to be of denser. So let's put it as 1.5, and I will make this as a denser medium, or sorry, a rarer medium. So that's such that I do have total internal reflection. So I will first start off with let's say 0 degrees. Now I'm increasing, I will be increasing, and I will put this marker over here. So just keep that in mind, that the refractive index for this particular medium is 1.5 and the refractive index of this medium is 1. That is, this is air and this is glass. And now I am moving or increasing the angle. So you can definitely see this part of the reflection is just because some reflective nature of the surface, whereas the total internal reflection will be the point where I will have no refraction at all. Everything will be cut off, everything will be totally reflected back. So I increase the angle. So again, a part of it is reflected back and a part of it is refracted. Again, increasing the angle of refraction. I'm about to hit 30. I just crossed 30. Then again, you can see that the angle of refraction is increasing, and it's now when I'm close to around 40 degrees, it's close to 60 or greater than 60. Again, I'm increasing. Now I'm just about to reach 90 degrees, which is, I think so, around 45. Alright, before 45. So uh, again, I would like to touch it in a more better sense. Okay, it's highly sensitive. Okay, so I can say that I think so, it's around 42, 43, 45 degrees. That is, it's just about to hit 90 degrees, and after that it will be total internal reflection. Everything is reflected back between this and this angle where it comes out. So you see this point where the refraction is totally cut off. This is the point of total internal reflection, and for the other angles, obviously it will be totally reflected back. So this phenomena is total internal reflection, and it's used quite a lot for, let's say, the majority use is its optical cable. So this as a whole is total internal reflection. I think so this simulation might have helped you along regarding the visualization of what is total internal reflection.
So if I'm to summarize what all the things which we have covered in this particular video, I can put few of the bullet points as these. First, we covered what is refraction, came out with a concept called refractive index. Then we sort of studied about the application of refraction, that is apparent height, lateral inversion, and also one of the most important phenomena called total internal reflection, which is actually a kind of refraction. Now that we have studied all those aspects associated with the plane surfaces, we will now shift our attention to spherical surfaces. That is, the next discussion is refraction through spherical surfaces.